The next part of our reaction stoichiometry unit is on basic stoichiometry. In this lesson we have two learning targets. We want to be able to identify mole ratios and balance equations, and also to perform some basic stoichiometry calculations. First of all, the question that probably comes up is, what is stoichiometry? Stoichiometry is the quantitative mass and mole relationships between reactants and products in a chemical reaction. I think a good way to explain this definition is to give you an example of a question that would relate to stoichiometry. For example, a question might read, if X grams of A react, what mass of B reacts with it? What mass of C is produced? So you can see this question is asking us about the mass relationships between reactants and also between reactants and products. This question could just as easily have asked about the number of moles that are reacting or are produced. That would also be stoichiometry. All of these calculations are based on mole ratios that appear in balanced equations. Let's take a look at the reaction to form water. In this reaction we have hydrogen and oxygen that are synthesized to form water. And notice the balancing here. We need 2 molecules of hydrogen to react with 1 molecule of oxygen to give us 2 molecules of water. The equation is balanced. Now consider this. What if I wanted not to worry about the number of molecules of hydrogen and oxygen in water, but the number of moles? I could actually just replace those words molecules with the word moles, and that would be the exact same thing. These coefficients in the balanced equation, the 2, the 1, and the 2, that you see here in the balanced equation, represent a mole ratio for the substances involved. This is because a mole represents the same number of particles regardless of what that particle is. So for example, 1 mole of hydrogen would be Avogadro's number of hydrogen. 1 mole of oxygen is Avogadro's number of oxygen molecules. 1 mole of water would be Avogadro's number of water molecules. So when we say 2 molecules of hydrogen react with 1 molecule of oxygen, we could just as easily say 2 moles of hydrogen react with 1 mole of oxygen. It would be the exact same ratio. Now, why this is important to us is that these mole ratios can be used as a conversion factor. So for example, we could just set all of these coefficients equal to each other. We could say 2 moles of hydrogen would equal 1 mole of oxygen, which would also equal 2 moles of water. And as we know, conversion factors are simply fractions or ratios that are equal to 1. So if I divide one of these by the other, it would be equal to 1 because they're all equal to each other. So those would be used as conversion factors. So we've identified mole ratios and balanced equations. Our next step is to perform some basic stoichiometry calculations, sometimes referred to as gram, mole, gram calculations, and you'll see why in just a second. And sometimes we might not have to do this whole process. That's why it says and combinations thereof. So that is the next step. Let's consider a reaction between hydrogen and oxygen to form water, actually the same equation we just looked at. Here's the question. If 2.50 grams of water are produced, what mass of oxygen reacted? So here's what we're asked to do. We're asked to find a mass of oxygen given 2.5 grams of water. Now if you consider what we just learned about mole ratios, I know that these balanced coefficients are a way to convert between one number of moles of a substance and another. So the first thing I want to do is I want to convert this mass of water into a number of moles. So that's just a gram to mole calculation. So I'd want to use the molar mass of water, so you can see here. So grams cancel, gives us moles of water. Now here's where the stoichiometry comes in. I need to convert from moles of water into moles of oxygen. We do that using the balanced equation, or the balanced coefficients in the equation that we see up here. From the chemical equation, I can see that 2 moles of water, notice the coefficient 2 in front of the water, would be formed from 1 mole of oxygen. Notice the 1 or the lack of a coefficient in front of the O2. There is my mole ratio from the balanced chemical equation. So moles of water cancel. Now notice I have moles of oxygen We can now convert that into a mass using the molar mass of oxygen, which would be 32.00 grams of O2. For every mole of O2, moles of O2 cancel, and now if you look at our units, everything works out. We're in grams of oxygen. We plug this in our calculator and we get 2.22 grams of oxygen. So to answer the question, if 2.50 grams of water are produced, 2.22 grams of oxygen have reacted. Moral of the story here, and really the point of this entire lesson, all stoichiometry calculations, they require the use of a mole-to-mole ratio from the balanced chemical equation. So in every single stoichiometry problem, you will have a conversion factor that looks like this. We have a mole ratio, and those coefficients that you use in that conversion factor come directly from the balanced chemical equation. Let's take a look at another example. Consider the reaction between aluminum chloride and sodium hydroxide. Here is the equation for the reaction. You can see we have aluminum chloride reacting with sodium hydroxide. This is double displacement, so we get aluminum hydroxide and sodium chloride. Here's the question. What mass of aluminum hydroxide can be produced if 0.287 grams of sodium hydroxide react? One thing that might be helpful for you to do in your problem solving is somewhere below or above the equation, wherever you prefer. Just jot in some numbers or some marks to indicate what it is you're trying to find. We're told we have 0.287 grams of sodium hydroxide reacting, so I write that under the sodium hydroxide. I'm asked to find the mass of aluminum hydroxide that are produced, so I have question mark grams under the aluminum hydroxide. Now, before we proceed with the problem, take a look at the equation. Do you see anything wrong with it? You might notice that that equation is unbalanced. In order to do any stoichiometry, we have to have a balanced equation. So, in bold letters, all caps, we must balance the equation first. Simple as that. Go ahead and take a moment and try to balance the equation. Okay, I assume you've had a go at balancing the equation. If you've done so correctly, this should be the balancing that you get. We should have 1 mole of aluminum chloride reacting with 3 moles of sodium hydroxide to give us 1 mole of aluminum hydroxide and 3 moles of sodium chloride. Now that we have a balanced equation, we can perform our calculation. Notice this is the same labeling ahead from above. We have 0.287 grams of sodium hydroxide reacting, and we're looking to find the mass of aluminum hydroxide that's produced. So this is just another dimensional analysis. We have 0.287 grams of sodium hydroxide. Like we saw in the previous example, we must convert that into moles. So we use the molar mass of sodium hydroxide, which is 40.00 grams of NaOH for every mole of NaOH. Notice grams cancel. Now that we have moles of sodium hydroxide, now is when we get to use our mole-to-mole ratio from the balanced chemical equation. So if I look at the equation, notice we have 3 moles of sodium hydroxide that are going to react to give us 1 mole of aluminum hydroxide. So moles of sodium hydroxide will cancel. If I put the 3 moles of sodium hydroxide on bottom, notice the 3 here going with the moles of sodium hydroxide for every 1 of aluminum hydroxide. Now to convert that into a mass, I simply want to use the molar mass of sodium hydroxide, which we see here. Notice your moles of aluminum hydroxide will now cancel. And if we take a look at our units, everything cancels to give us the grams of aluminum hydroxide that we were looking for. We plug it in our calculator, and we get 0.187 grams of aluminum hydroxide. Again, just summarizing here, notice this is a gram, mole, gram calculation. I mentioned earlier I would explain why this is. Simply because we start with the unit grams, we convert it to moles, we convert it to moles of a different substance, and then to grams of that different substance. So thus it's called a gram, mole, gram calculation. Next example. It asks us to write the equation for the reaction between magnesium and hydrochloric acid. Go ahead and pause the video, try to write that equation correctly. So you've had a go at writing this equation. This is what you should get. Magnesium with hydrochloric acid. Notice HCl is the formula for hydrochloric acid. This would give us magnesium chloride. Notice this would be a single displacement reaction. And it also give us some hydrogen as well. Notice the balancing, we need 2 moles or 2 particles of HCl to go with 1 particle of everything else. That would make it balanced. Alright, here's the question. What mass of hydrochloric acid is required to completely react with 1.2 grams of magnesium? So notice here we have our labeling for what it is we're trying to find. And notice in this problem, we're asked about the relationship between 2 reactants. In the previous 2 examples, we were asked about the relationship between how much reactant compared to how much product. The problem has not worked any differently. It's the exact same thing. In this case, it'll again be a gram, mole, mole, gram calculation where we're going to start with the mass of magnesium, 1.2 grams, convert that into a mass of hydrochloric acid. So like we did before, we need to convert our mass into moles. Molar mass of magnesium is 24.31 grams. Now we'll use our mole ratio from the balanced chemical equation. Notice we have 2 moles of hydrochloric acid reacting with 1 mole of magnesium. So there is our balanced equation and how those coefficients would work in the conversion factor. Notice here the importance of the labeling of the substances, not just the units. This is something I could have mentioned earlier. If I just label this moles and not moles of magnesium, I'm going to have a very difficult time figuring out which coefficient to put where in my mole ratio conversion here. So notice the importance of that. I can see that the 2 has to go with the moles of hydrochloric acid, and without labeling it HCl or magnesium, I would have a difficult time remembering where to put it. Alright, now that we're in moles of hydrochloric acid, we can convert into a mass of hydrochloric acid. So the molar mass of that is 36.46 grams. Your moles of HCl cancel, and this will give you an answer of 3.6 grams of hydrochloric acid. A second question to go along with this problem. We want to determine the mass of magnesium to produce 0.015 moles of hydrogen. Notice here we are given a number of moles of hydrogen. Okay, we want to produce 0.015 moles of hydrogen, not grams. Now, the effect that this has on our problem solving is it actually simplifies it. Previously, in the previous examples, we've seen gram, mole, mole, gram problems. Well, here we're already given a number of moles to start with. A very common error I will see students do here is they'll try to use the molar mass of hydrogen just because they're so used to using a molar mass to start with, like we see in the previous example. But remember, the reason we use that molar mass is to convert it into moles. Well, we already have a number of moles. So the first conversion factor I can use here is actually that mole to mole ratio from the balanced equation. So if I look at the balanced equation, I can see there is 1 mole of hydrogen produced for every 1 mole of magnesium that reacts. So there is my mole ratio from the balanced equation. So moles of H2 cancel. We have moles of magnesium. Now I can convert that into a mass by using the molar mass of 24.31 grams per mole. And we have solved the problem to give us 0.36 grams of magnesium. All right, several examples here. I'd like you to practice it on your own now. As always, I'll have the problem here. Pause the video, try it yourself, and then play it through and see if you did it correctly. All right, consider the decomposition of trinitrotoluene, which is known as TNT. You might recognize that as a main component of dynamite, because it is. So here's the equation. Your TNT formula is seen here, C7H5N3O6. And you can see our decomposition products. We get some carbon monoxide, some nitrogen, and some hydrogen. Also notice the equation has already been balanced for you. So in this case, you would not need to balance it. All right, first question. What mass of carbon monoxide can be produced if 3.65 grams of TNT decompose? So here's what we're trying to do. Trying to get to grams of carbon monoxide, starting with 3.65 grams of TNT. So our first conversion, we need to convert our mass of TNT into a number of moles. So I want to use the molar mass. That is 227.15 grams of TNT for every mole. Now that we have moles of TNT, we want to convert that into moles of carbon monoxide. From our balanced equation, we can see there are 12 moles of carbon monoxide produced for for every 2 moles of TNT that react. So there's your conversion factor. And then finally, to convert that into a mass, we want to use the molar mass of carbon monoxide of 28.01 grams. Notice all your units have canceled now, and this gives you 2.7 grams of carbon monoxide. Alright, hopefully you did that problem correctly. Here is a second one to practice. How many moles of hydrogen are produced when 100 grams of carbon are produced? So here we're asked to find a number of moles of hydrogen. Notice the difference from the previous examples. Before we've always been asked to find a mass. And then we are producing 100 grams of carbon. So starting with 100 grams of carbon, I need to convert that into moles. As we know with stoichiometry, we always need our amount of substance in moles. So converting that to moles using the molar mass. Now I can look at my balanced equation. I can see that 5 moles of hydrogen are produced along with 2 moles of carbon. So there's my conversion factor. Notice the 2 moles of carbon go on bottom, so the moles of carbon unit will cancel. And that's it. Because we're asked for a number of moles, I don't need to use the molar mass of hydrogen to convert that into a mass. I just plug it in my calculator, and we get 20.82 moles of hydrogen. Alright, in this lesson, we have identified how mole ratios in balanced chemical equations can be found. And then we have also looked at how we can perform some basic stoichiometry calculations, sometimes known as gram, mole, gram problems, or some combinations thereof when we don't need to use the entire problem-solving series.